Hey everybody, welcome. My name is Jeremy.
And I'm Bill.
And you are watching this course, this MBA course on demystifying LINQ. So LINQ, L-I-N-Q, not to be confused with all the many other ways of using the word link. Demystifying LINQ, if you are in any way mystified by LINQ, if it's a mystery to you in any way, then you've come to the right place. So we're going to go ahead and dig in. First of all, we're going to introduce ourselves. Sitting next to me, Bill Wagner.
Good morning. Bill Wagner. I am a C# MVP and a member of the C# Standards Committee. I wrote Effective C# and More Effective C#. And I love the things that we can do with the language with Language Integrated Query, which is what LINQ stands for. And today we'll talk about how it works internally and give you a really good understanding of, when you write that code, what exactly is it doing underneath the covers in all those different places.
So Bill, what you're saying is you've used C# before.
Yes, I've done a few of these things.
A little bit of experience there. And I'm Jeremy Foster. I'm a technical evangelist at Microsoft. I've got quite a long history with C# and a deep appreciation, might I say, a love for LINQ. I actually write a lot of, if you follow me online, you know that I'm writing a lot of JavaScript these days, but that says nothing about my deep love for C# and specifically LINQ. I'm an author, presenter, hacker, coder, maker. I'm having a lot of fun with the Internet of Things these days. That's just a great space. And you can find me online anytime you want, codefoster.com, and on Twitter @codefoster. And yeah, so that's Bill and that's me. And we're going to kind of give you an overview of the course for the day. What is it that we're going to be learning about today?
Okay, so we're going to break apart LINQ and understand how everything inside of it works. So in the first module, we're going to look at enumerables, those methods that you write and the things that you do that produce sequences and how they work in LINQ. And sequences are different than collections. We're going to be very careful about using that word sequence. It's not a collection. It's not a whole bunch of things. It's something that creates something for you when you need it. Then we're going to go through in the next 3 modules, and we're going to show you how different methods you probably use in LINQ are actually built, what they do underneath the covers, and how they're put together, and how those little building blocks that make up a LINQ query talk to each other, and how they pass a sequence through all those little operators. Then later we'll look at the query syntax. LINQ has this mechanism where there are keywords in the language that map directly to certain methods. So when you write certain things in a LINQ query and it comes back, it maps to a particular method that should be available. And we'll talk about exactly how that mapping works so that you can see and decide whether you prefer the query syntax in certain places or whether the method syntax works better for you. And then at the very end, we'll look at some of the performance consideration. LINQ's a very high-level abstraction. There's a lot of things going on underneath the code that you write. And those things have a lot to do with how it's going to perform. So there's some things we can do to make LINQ faster, and there's some things we should just avoid, especially in really super performance critical places where we might want to just be closer to the metal just for those performance considerations.
Now, what if you're a person that's on the job and you are pretty experienced with using LINQ? You've used a lot of the operators before already. Is there going to be some content that's still helpful for those folks today?
You know, I think so. I think it really helps to understand exactly how things are built inside. So we're really going to break it apart and look at, what happens inside some of these methods and what is the design goals around them. So you'll have a better chance of picking the right ones when you're using different LINQ methods.
Okay. All right. So should we go ahead and start with a look at the concepts around enumerables?
Sure. Let's do that. So one of the main things that we would see in enumerables, the idea behind this, in this first module where we're going to look at enumerables, is that what we have is we have a set of sequences. So everything in LINQ operates on some sequence of elements. And what we're going to do is we're going to separate those sequences from the algorithms that they work on. And we're going to write these methods that know how to generate the next item in a sequence when something asks for it. And we'll look at code that goes about and generates sequences. So when we start with things, we can see, well, how would I generate a sequence? What happens there? We're going to implement an enumerator that knows how to take something coming in or take some input and create an enumeration. We'll look at a little bit of the mechanism. We'll introduce the mechanism of separating how we traverse a collection or traverse a sequence with what operations we want to create with that particular algorithm. And then finally, we'll look at something called lazy evaluation, which the people who've used LINQ before probably understand. But if LINQ is something you've only played with generally, you might not get.
Yeah.
There's times when we introduce code and we write it, and we think it's producing some data structure, but with LINQ that's not necessarily true. It's really producing a series of objects that knows how to create the sequence when you ask for it.
And the advantage to that is what?
The advantage to that is we can compose all the operations to create a sequence and then only actually ask for the sequence when we need it.
Yeah.
And that I think makes a huge, huge advantage.
I think one of the times when that was a big advantage to me was whenever I wanted to do conditional parameter or conditional statements in a where clause. Like for instance, I wanted to do some sort of a filter of my data, but then conditionally I wanted to add another filter. And then maybe conditionally I added another filter, and I haven't actually affected any data yet.
Yes, right. And that's even more critical when your actual data store is not local.
Yeah, right.
Or not in memory.
Yeah.
It's a database, or maybe it's a web service, and you can compose all those operations and then make that one query to get the data from the remote store. So you're telling the remote store do all of these things and then bring back just that final answer instead of bring me back this collection and I'll do all this local processing.
Yeah, right.
So that kind of thing can be a huge impact on the way, especially as we're writing these larger cloud-based distributed systems, where we have our web tier and some business logic, and we have a data store over here, and we might be talking to another web service to pull other data in, and all those things are on different machines. The ability to pass around this recipe to generate a sequence to the other machine and not constantly be having that network traffic is huge.
Well, Bill, I think a lot of people actually think about enumerables as collections, and so I think some clarification today is going to be super helpful.
So one of the things that I do, if we can kind of bring us all back to what we're doing here live, is one of the things I do with when I speak with this at conferences is I use a deck of cards to explain to people the difference between those. Right? So if you imagine that I'm representing this algorithm that produces something in a collection, right? What would happen is I would do all that work, and if you asked for the collection, I'd hand you this whole thing, right?
There it is.
So now you have everything, you've got the whole deck of cards. LINQ doesn't work that way. I don't have to do all the work to produce all of that. So if this were a LINQ thing, and you were going to start processing a sequence, well, what your code would do would be ask for the first element. Right? And all I do is I just hand you one. Right? So there you have one, and you can do whatever you want with that. And then when you're ready, you ask me for the next element, and I would hand you one more. And when you're ready, we ask for the next one. Maybe it's got a where clause. The next three don't work. They don't pass the where. Here's this one, and so on. Right? So it's this idea that we're actually pulling the sequence through any series of operations rather than making all that work and doing all that stuff right from the beginning and then passing a whole collection along.
Yeah, and I can imagine that there are certainly performance memory impacts when you hand me an entire deck of cards. This is 52 items, but this might be 52,000 items.
Right.
I can't take the whole thing all
right, and memory is where that really comes in. From a performance standpoint, unless we're talking parallel link or something where we can put each one of those different operations on a different thread, the CPU performance isn't a huge deal, but from a memory composition standpoint, it can be, right? I can have a sequence here, and if I only have to hand you one or two elements, we only have to generate those first two elements, right? And we'll get into that as we look at some of the methods in LINQ that only return part of a sequence, or only have to look at part of a sequence.
Yeah.
Right? And when we get into things like really big data scenarios, I can work effectively with an algorithm that operates on an infinite sequence that never ends. As long as I don't need the whole thing, right? If I only need certain elements and I don't need to examine the whole sequence, it doesn't matter if it's how big it is. And that can be huge in terms of, as you say, the memory performance, what happens with the garbage collector, and all those sorts of elements. So that's kind of where we're going today, is to look at what happens inside all of this and how that magic works. So with that, let's look at what we mean by implementing an enumerator and how I would go about what is an enumerable, what happens, what code gets generated, and how would we create or consume one of those. So let's dive into some code here. And what I have on the screen is a method that generates 100 strings. So it should look really familiar to anyone who's used C#. I create a new collection. Here it's a list of strings. I'm going to count up to 100, and then I'm going to go ahead and convert that number up to a string, and then just return that entire collection. Okay? And now, here we have this code where I'm just going to for each it, I'm going to look through it, and I'm going to use that sequence. Okay? Now, before I can write that first element out, I would have to generate the entire sequence, right? So if I just run this one right now, it's going to come up. We're going to grab that, run that simple application. It's just going to print the numbers 1 through 100. And there we go. You can see 1 through 100 pops up on the screen, and we're done. Okay, now, if I were to change this 100 to something like int.max, okay, I'm not going to run that because we'd really be here all day. It's going to run forever. That's that idea of just if we're creating just an absolutely huge string. But now, let's say I want to generate a sequence, and I'm going to go try to find different values from it. And I want to generate it lazily in terms of when am I going to go ahead and actually use those? I'm only going to generate a value when someone asks for it. Well, right now I'm just going to show some of the syntax. And C#3 with LINQ added this yield return concept to create an enumerable. So I can return, wow, we're getting a different, we may have to stop and start again.
Can we try hitting Windows space and see if that brings up an option to change your language? Looks like, yeah, go ahead and hit it again until English is selected. There we go. All right, now that should do it.
Wow. I have no idea why that happened. So yield return 1, you can say yield return 2, yield return 3. So now the way this executes is when I ask for the first element in this collection, or this sequence, we'll execute that yield return 1, return that first, then we'll print it out, and then when we ask for the second one, we'll leap back into this method and execute yield return 2, and then bring that back up and write that one to the console, and then we'll leap back into this method again and execute yield return 3.
So my instruction pointer, if I were to look at this from an assembly point of view, does my instruction pointer actually jump into the generated strings method and back out, and then back in and back out?
Kind of, sort of. Okay. We can think of it as doing that, but the code that's actually generated is what's generated inside this generated strings method now is it creates a class that knows how to generate the next sequence when we ask for it, or the next element in the sequence. So if we're familiar with IEnumerable, it has one method on it called getEnumerator, which returns an object that implements IEnumerable, or excuse me, IEnumerator. And that IEnumerator interface has 3 methods on it: current, move next, and reset.
Okay.
So to start a sequence, I call move next. So now I'm going to point at the first element of the sequence. If I look at the current property, it'll return that first value. And anytime I call move next, it moves or generates the next item in the sequence. If I call reset, it puts it back to the beginning of the collection. Right.
So this is a little bit like the C# async await pattern, where it feels to me like I'm just writing simple code inside of a function, but what's happening behind the scenes is the generation of an object that has some rich functionality, some methods.
Exactly. That object has all that rich functionality embedded into it, and it knows how to generate the next sequence.
Great.
In this case, it simply returns a constant, so it would know how to do that. But walking through this in the debugger can sometimes be instructive. So if I put a breakpoint here on that console.write line, and I'll put a breakpoint on each one of these yield return statements. And if I press F5 to watch and see where we, and I have to comment out these other values because since I'm using yield return, I can't have both a yield return and a return.
Okay.
So we'll remove that old code, and now run through this version. You can see the first thing we're doing was write that yield return. Great. Hit F5. We're going to write out that first string. Now we're back inside this other method, yield return 2. Now we can't really just leap back and forth inside methods. So as we said, it's generated this object that then knows how to generate the next item. Pop back up, console.write line, pop back down, yield return, and then we'll write that last item. Okay? And where it's really useful that the compiler does all of this work is if these were more complicated methods and I were to do something like try, have all those yield return statements, and then if I had some work to do inside a finally clause,
Yeah.
okay, and this is where that analogy of saying we leap back into the method kind of fails. When I exit a method, what I would do normally is the code is generated to execute everything in the finally clause, any cleanup, anything of that nature. If I was, say, reading from a file and this finally clause closed the file, well, when we hit that yield return, we're returning from the method, technically. We move back up to the calling point in the call stack and we execute what's up there. But we can't execute the finally clause yet because that would close our file and we wouldn't be able to generate it anymore. And that object that gets returned knows that it's still going to continue to execute and access that file to get at other elements in the list. So therefore, it won't execute the finally clause. And that object has some more complicated code to know that now when it's all done, now execute the finally clause. Once we've closed the enumerator and we've finished examining the entire collection. Right? So there's some interesting code to handle inside that object to be able to do all of that work.
It's beautiful because it seems like the end result is to give us a syntax that makes it really nice for the developer. Nice to write, but then also nice for me to parse the code that you've written, for me to understand it and be able to maintain it.
Right. And then where this gets somewhat more interesting is the kinds of things that we can work with now is if we dive into this. Right now I've just got it yield returning 3 different strings. Okay. Well, now we can take these out, and instead of that, let's go back to where I was trying to generate that whole list of 100 different elements. So, instead of generating that entire collection, I don't even need a collection here. I can now just say yield return and now I'm going to be generating that sequence. Okay.
Now, do you ever use the yield keyword by itself, or do you always use yield return?
If I have yield by itself, that's not a keyword. So notice it's black right now.
I see.
And without a return in its place, now it turns blue.
I see.
And this is one of the really interesting things that's grown in C#. And LINQ was where this first really came into being in a lot of the ways that they were adding keywords in the C# language. So LINQ came about in C#3. So there was already a lot of code out in the field that was written in C#1 and C#2. So all of the keywords that were added for LINQ are what's called contextual keywords. They only apply as that kind of a keyword if, in fact, they're in the right context. So I could even say something like var yield equals 3, right?
Interesting.
And here yield is just a number, it's just an identifier. It's not in the right place, it's not followed by return, and that's why it's perfectly valid as a symbol.
It's pretty interesting.
I could even then do something, it won't compile because of the return types, but then I could return yield, and at least the parser knows, you know, this is a return value and it's a number.
Could you yield return yield?
Could I yield return yield? I bet I could. I'd have to turn this into a string.
There you go.
There we go. So I can yield return yield. I can do anything that I want. It knows that that keyword.
By the way, don't try that at home.
No. That's the kind of thing that would show up on a Stack Overflow question. Right. So now we can generate those strings in different ways, and we generate them now only when needed. So now I could do something where maybe I don't feel quite so bad. I'm going to say we're going to do int.maxValue here and generate all kinds of things. And instead of doing a for each here on the entire sequence, I'm going to rewrite that loop and just say for int I equals 0, I less than 100, I'm going to say var sequence equals generated strings. And here I'm going to do a write line of and then we'll say var iterator equals sequence dot get enumerator, and we'll say iterator dot current, and I'm going to need to put braces around this to do my own enumeration, and I'll say iterator dot move next. Okay.
And You need your I++.
I need my I++. Yes, I do. So now I'll be putting out the first 100 items in there. Now, if I wanted to make this production code, what I really would do is I would say if iterator.moveNext, do that, and then else will just break out if this sequence didn't actually have 100 elements.
Okay.
So now I'm looking at the generated strings. That's an I enumerable. In order to enumerate it and see what it does, what's inside it, and see how that works, I'm now going to get an iterator. And now in order to look at the things on that iterator, I need to call iterator.moveNext. I've now moved to the first element in that sequence. I'll write that one out, and then I can move to the next one. Right? And I don't feel bad executing this code because it's going to stop at 100, even though my generator here would generate however many max in is in a 32-bit system. It's whatever really large number that we'd be here for a long, long time. Right? So now we've broken apart this thing. We have a number of different things that we might want to do.
Now, you just made that code block messier, but that's just because you're not iterating the entire thing.
Right.
You're choosing.
I'm choosing what I want to do.
100.
And what I'm doing here is I'm actually creating it, and I wrote all that ugly code just to show what happens internally and show the things that are generated by an enumerator method.
But you could still use a for each block.
Absolutely. I can use the for each block. If I wanted to generate the whole sequence, I can do any different kinds of things that I would like there. So with that, let's look through and get to a little bit of where we would want to do in terms of, let's separate that enumeration from the algorithms. So we've got a different kind of things that we want to do with this. This code gets really messy, in part because I'm trying to do all this work to look at what the sequence is doing, right? It's got all these things in terms of what kind of a sequence it is. I've got this for each loop. I'm looking at different areas inside of it. So one of the things I'm going to do throughout the day with all the different demos that we have is I've got a GitHub repo that shows all the code that we're working with. The things that I'm doing live right now, I'm just going to discard. They're mostly in the repository as well. And everything is labeled with a set of branches. So if I were to look at a branch here, the next branch, it's going to be pretty similar to some of the things that we've already put together. And now let's leap forward one more roll. If I look at generating things in my loop, all right, so I've got this part in place where I said I want to generate just 100 strings. And if I wanted to have this in place, now I've got that loop that I was going for. Now let's just say that while I is less than int.max, if I wanted to generate everything, and if I wanted to write this really well to be able to just execute that line of code only when I wanted to, I could use one of the link methods and say item.generated strings, and we'll talk about this particular method later in the day, and I can take 100. So now I'm going to say, instead of looking at this entire sequence, just only give me the first 100. Okay? So we put that in place, and now I'll get
the first 100.
And it's quite a bit
nice
cleaner.
And clean, yeah.
Right? So now these algorithms, these bits like take or other methods, allow me to just get some things that are pulling only those in place.
And this link method, take, worked on your generated strings because it knows that the return value of generated strings is an I enumerable.
Right, right. And then take, it's an extension method. Its first parameter is that I enumerable, and it works through each portion. Okay. Now let's say, right now I'm just generating these hard-coded strings. And this generator right now, what it does is it's really constrained to only generate strings that match numbers. Another key concept in LINQ is this idea of really separating, traversing a sequence from what we do with that sequence. Okay? So for the last demo in this particular one, we're going to introduce a couple concepts that you've probably used if you've used LINQ, or you've certainly used if you've used LINQ, but you might not understand exactly how they work and how the things work inside to do that. So let's say I want to generate any kinds of strings, and I want the caller to be able to specify how they want to generate that string. Okay? So I'm going to add a parameter to, I'll just make a second overload of this generated strings method. And what we're going to add to that generated strings method is I'm going to add a parameter that's a func of t. And I'm going to call that my item generator. Okay? This now becomes, instead of IEnumerable of string, it's now an IEnumerable of t. And now the method needs that generic modifier on it to say it's generated strings of t. So it's going to return a func of t. And now notice that because this is returning a string, I need to modify this. So now what it's going to return is just a call to item generator. Okay? And now if I want to generate different things here, if I want to say, what I want to do is do that same generate from 0 to 100. Right up here I could put that in I equals 0. And here we're going to introduce a lambda, a method that takes no parameters. And what it's going to return is I++ dot toString. Okay? So now the parameter to this generated strings method is going to execute that code, and I'm passing in this code into that enumerator method to say that's how you generate the strings.
You're not giving it a value, you're giving it a function.
I'm giving it a function, exactly. So I can now, it'll do the same thing here. And now we're going to do an interesting little trick. So now I'm going to say, just say var sequence equals this generated strings I++, and so on. And now I'm going to say for each item in sequence, we're going to generate that sequence. Still want to only take 100 of them. Okay. Oops. But now I can do an interesting trick. If I run this code right now, it does exactly what we did before. I've just separated out that variable. I get the numbers 0 through 99. But if I now change this to say, after I've defined the sequence, I'll say I equals 50. Okay?
Okay.
And now if we run this, what do you think is going to get printed out?
50 through 149.
50 through 149, exactly. Because what happens is that generated strings doesn't produce a collection, right? It produces a sequence when you ask for it. And because I don't ask for it to the for each loop, we print 50 through 149. Now if I change the internal implementation here not to use this yield return, but rather to go back and say, and create a list here. And then instead of a yield return, what I'm going to do is do an rval.add item generator. And then if I return rval, okay, now I'm generating the entire sequence inside this method.
Returning it all monolithically.
Returning it all monolithically back up. And now this same code, when we run it, notice how there's a noticeable gap here.
Yeah, it's taking some time. It's got to process.
I think I left that max int value in there, so we'll close this.
We're in big trouble.
We don't have that much time. So we'll leave this at just 100. And now we see it pop through and we get that one number back out. And it still generates the 0 through 99. So I don't like that at all for all those different reasons. So we're going to go back to the yield return. Now that's a relatively simple operation on this, and that has a lot to do with, most people understand that and kind of see that, and the natural way we write code would usually work correctly here. However, where developers sometimes can get in trouble is if something inside this loop when I'm doing the enumeration modifies any of the variables that gets grabbed inside the closure. So if inside here, if I now do I plus equals 10, okay, now we're going to get a totally different set of numbers. I'm going to remove the I equals 50 here. So we'll start at 0, we're going to increment to the next element, and then we'll pop forward again. So if we run through this one, we see now I'm getting these numbers that start at 0, 11, 22, 33, and so on. It keeps running at a much bigger set of numbers. We're driving through these in such a way that what we do is we generate the next item, and when we generate the next item, we're now going to increment it by 10, and then when we generate the next item, it keeps moving forward by 11 each time. And because of the order that it's put in place, the first one is still 0. So the very first thing we do from that enumerable is we take that enumerable, generate the first item, and we call move next to point to the first element. And then once we call move next and point to the first element, we'll return that 0, increment it, and now we're pointing at 10. And then we increment it again, and then we get the 11. So we're putting each one in place slowly but surely as it moves on. That's where I see people that may be less familiar with exactly how LINQ works inside, where things can occasionally get tripped up. They've created this recipe for how to generate a sequence, and then while they're enumerating it, they may modify that recipe unknowingly.
Yeah.
Or knowingly but not knowing what kind of an effect it has. So this is some of those big concepts. The idea behind here is any time that we're generating a sequence inside LINQ and using these kinds of methods, those enumerables only generate the items as you ask for them. Right? Any kind of transformation you make to how they're generated before you ask for them has absolutely no effect on any data structures that's already in place. It will affect what you get back when you ask for it. Okay? So that's that elemental core sequence for enumerables. We're really going to want to make sure that we understand that, and every single part of that is going to be part of what we work with in LINQ.
Yeah.
And then to go back to separating that algorithm from how we generate things, now in this last version, where I have this generated strings with a func of t, I could do anything here to generate different kinds of items. So instead of generating strings by calling i.toString, I can say, let's do just datetime.now. Okay. Simply generating what's coming out. Modifying I really is going to have absolutely no effect anymore because I'm not even using it. Okay. Now we're just going to print out the current date all those different times. We can put more interesting modifications here. So, and even work with a local variable. So if I can say var today equals datetime.now. And then inside my generator, I can do a little bit of work on that. I can now say, I'm going to add curly braces so I can put a few more lines in here. And I'm going to say today equals, or we'll say plus equals time span dot from days. We'll move forward a week. And then return today. Okay, so now I'm going to take today and I'm going to add a week to it, every single item as it works through that sequence. Mm-hmm. We have the flexibility to do that, and you can see we start today when we're recording this, and we keep moving forward by a week.
Yeah.
Wonderfully cool. So all of that keeps moving forward. And I've separated that idea of just generating a sequence for the recipe of how do I generate a single item in the sequence.
Can you tell folks that may have a conceptual understanding of streams, how sequences and enumerables differ from streams?
How do sequences and enumerables differ from streams? That's a really good question. So if I were reading things out of a stream, I continue to grab the next character, grab the next item. And in fact, they are conceptually similar in a lot of ways. If I open a stream, I can ask for what's next. Depending on the kind of stream, in files I may be able to move the file pointer forward and backward and do random access. In a sequence, typically you can only ask for the next element. So in terms of, say, a file stream or that's coming in where you can read only one character at a time, that would be very analogous to this kind of enumerable. And when it comes back in, then we're going to get just that one element. Differences would be that the stream, might be a little more brittle in some ways, in that if I change the elements in a stream, especially if I write to a file, you have to lock it and things of that nature. Using this kind of loose coupling, that sequence may be getting modified as I'm looking for the next element, depending on how I'm coupled to grabbing the next item from a sequence.
I see.
Right, further through the back end of what's generating it. But that is a very, very good question, and that kind of programming is a very good model to have in your mind of grabbing the next thing from a stream or from a web request or from what have you, and then now processing that in some way. And a really good analogy with that is think of processing a web request. Like if I go to a website and I'm pulling down a page, usually what will happen in the browser is it has to see all of that page before it can start rendering, right? So it has to get the tags, get everything parsed, get that full model of HTML, and then it can start rendering. So let's ignore things like images and whatnot, which are a separate request. So it has to grab all the HTML, read the entire thing, and now it can start to display it. Contrast that with streaming video, and you're watching a streaming video, maybe this course, and instead of downloading the entire module and then starting to play bytes, as soon as there's enough of the stream in place, it'll start playing, and as it's buffering more of the content that comes down, we'll start playing the video that in the browser that you're trying to examine. That's a really good analogy to how Link works in terms of pulling content in place. I'm streaming things from some data source, and as I get enough of that data to do the work I want to do, then we can start displaying it, right? And I think that's a really good mental model to have.
Yeah.
Okay. That's primarily the demos for the first module. The big thing that we want to get out of the first module is this idea of an enumerable. Enumerable is actually an object that comes into place, and it's not a collection. It's an object that knows how to hand off that very next item in a collection and bring that collection in, or bring that sequence, hand you the next item when you ask for it.
So most of the stuff that you've shown us so far, Bill, is eventually going to be hidden from us.
It's eventually going to be hidden.
We don't have to deal with.
Right.
We don't usually, unless we're creating our own, we don't usually have to worry about the concept of the enumerator or the enumerable, because we have an object that implements that interface.
Right.
And so it just naturally can act that way. So we can just start tacking these link functions on top.
Absolutely. And that's where we'll actually use these concepts ourselves. Is Link has a grammar built in for any number of operations on a particular sequence.
Yeah.
If you want to extend that grammar for your own domain, then you'll start to write methods that make use of these particular elements. Or if you have a particular very specialized kind of data structure, you may want to write your own implementations of certain elements in the link grammar to generate sequences from your data structure. For instance, you can think of, you mentioned that you really like Internet of Things and things like that. I could create an enumerable, say, for my Internet of Things thermostat, right, that generates readings on exactly what is the thermostat set to and how comfortable, or what temperature is it reading right now. I could have a sensor that does that. And then if I were to pull that enumerable, I would get what is that sensor reading at this point in time.
And,
right.
And just like you were saying before, sometimes this query expression, this query is going to end up having to go to a database. Well, in the Internet of Things, oftentimes you've got very small connections, and so you want to make sure that you're really efficient with your queries.
Exactly, and then you'll go look at what data am I pulling off from that particular thing on the Internet, and we'll grab just those elements. Yeah. And it may be formatted in a certain way. You may have some elements that are compatible with Link that grabs whatever data off a port or however it's formatted there in whatever binary format that particular device uses, and surface it maybe as a JSON object if you want, or what have you. Right? So that would be one way when you would actually dive into some of these. Conceptually, it just really helps to know a sequence is not a collection. Conceptually, it is just how I access the next item in a sequence, or ask, is there a next item in the sequence, right? And I think that's the main key we want to get through. any of those analogies that work for you, whether it's that card deck analogy, the Internet of Things analogy, the file stream analogy, any of those is a good way to look at that sequence, right? And with that, then let's continue reviewing the different content that we have. So we looked at putting those sequences together. We've got traversing a collection. The link enumerables may be traversing a data source, or they may be generating their own. The ones that we wrote here in this first module generate a sequence. As we start implementing our own implementation of how link works, we'll start traversing sequences that are handed to us. So we'll keep using these generators. We'll write another one. We'll have a little fun working with those and seeing how the internals of link are built. And we'll drive through those different areas and get a deeper understanding of exactly how the grammar works, how the elements work, and how those concepts work. We'll really drive into areas like this lambda expression right here, which is basically making a small function, treating it as an object, and then passing that object around that knows how to execute that function at some later point in time. For people that are used to JavaScript, that's a very, very fundamental concept in the JavaScript language, this idea of passing functions as parameters. Here it is in C#. I've had it as lambdas for some time, and we've probably been using it without worrying exactly how it works.
Yeah, right.
It works exactly the same way as it does in JavaScript or TypeScript. And those are the main concepts for the first module. I think with that, we'll take a short break. We'll come back and we'll start implementing our own version of Link to understand how these building blocks are put together and how they all build on top of that enumerable.